All right, so what is the deal with all these rules for exponents? So this video is going to try to kind of explain why they work the way they do. I must admit that over the years, I've just sort of accepted and applied these rules as they were. But today's student, being as intelligent as they are, love to ask the question why. So this video is an attempt to answer those questions. All right, so when you look at this particular formula card, it can be a little bit overwhelming, and I can understand that. But usually what I say is, remember these 5 right here, and then these other rules, specifically special rules for negative exponents, these rules will fall into place based upon these other ones. So if you can remember these will all make sense and fall into place as you work through these things. Based upon that same logic, I'm going to explain some of the more abstract rules, specifically the zero exponent rule and the negative exponent rule, based upon these rules. Remember, in math, all these rules must be consistent and support one another, okay? And at the end of the video, I will explain some of the less abstract concepts. And but I want to put these more abstract ones up front in the video to perhaps capture your attention before I lose your attention. All right? All right, so looking up here at these two rules of exponents is usually where the questions start. You got the zero exponent rule, and then you got this other one that's kind of unusual to think about. Specifically, how 0 to the 0 is typically referred to as being undefined. All right, if you were to go to Google and type in 0 to the power of 0 proof, you would undoubtedly come across a lot of complicated mathematical proofs. Specifically, you also see that they refer to 0 to the power of 0 as an indeterminate expression, and that an indeterminate expression with those, it is impossible to assign a particular value to them. Let's really not go there. Let's go with this rule here and say that it is undefined. Okay, so let's begin to explain these two rules. But to explain these rules, we need to bring up one of the other rules. And that one is the quotient rule for exponents. And basically the quotient rule, as it says here, if you got a and it's some non-zero number, and then you got m and n, which are integers, we can write this way: a to the power of m over a to the power of n equals a to the power of m minus n. What this is saying is, if we're dividing powers of like bases, a is our like base. We keep the same base, a, but we subtract the exponent of the denominator from the exponent of the numerator. As you can see, m minus n, okay? So based upon that, it's best to explain and demonstrate this rule by using numbers. A very simple arithmetic problem, I suppose. Consider 3 squared over 3. This is actually 3 times 3, right? Because an exponent means you multiply that base times itself that many times. So we got 3 times 3 over 3. And then there is the fundamental property of rational expressions. These 3's would cancel. 3 divided by 3 is 1, so we end up with 3. All right? But let's use our quotient rule here. That also equals, keeping the base 3 squared minus 3 to the first, because any number can be raised to the power of 1, and that is that number. So 3 squared minus 3 to the first, 3 squared minus 1. We're subtracting our exponents, keeping the base. We get 3 to the first, and again, that is 3. All right, so if you're wondering about the fundamental property, basically it's this one right here. A over B equals AC over BC. The idea here is that these C's cancel out. That's why you get A over B. All right, and if you're wondering about this one, let's just look at this in a more simplified or a different approach at arithmetic here. All right, 3 squared is actually 9. So we keep the 3 in the denominator. 9 divided by 3 is 3. So our quotient rule holds based upon everything that we know about mathematics so far. All right, so now let's start to explain or justify these two concepts, the zero exponent rule and the fact that the expression 0 to 0 is considered to be undefined. Okay. Let's start. Well, of course, we've got to start here with our knowledge about the quotient rule for exponents, right? Which you already talked about. So let's start here. A to the 0 equals 1, right? We've said that. All right. And we also know that A over A is 1 because any number divided by itself is 1. And then we also know that any number can be represented exponentially by taking that number and raising it to the first power. So A over A is A to the first over A to the first. Now let's apply the quotient rule here, which is A, the base, keep the base, subtract the exponent of the denominator from the exponent of the numerator, and we get A to the 0. So there we go. It does hold with our rules. Now let's go with this other concept about 0 to the 0 being undefined. So remember we said that we can write any number exponentially by raising that number to the first power. And then you might look at this, you're like, wait a second. By the way, 0 to the 1 is 0. You can try that on a calculator if you want. But you might look at it and say, hey, wait, you got division by 0 here. That is undefined. Well, exactly. That's where we're heading here. But let's just for fun apply the quotient rule to this particular expression. Let's keep the base, subtract the exponent of the denominator from the exponent of the numerator. So we got 0 to the power of 1 minus 1, which is 0 to the 0, which we said was undefined. And that is consistent with our definition of division by 0, which is undefined. So things are supported by our rules so far. All right, so let's explain another rule that is a bit unusual to consider and sometimes generates a lot of questions. But anyway, it's the negative exponent rule. So if we got a natural number n and any non-zero number a again here, we take a to the negative power of n, that is equal to 1 over a to the n. To explain this, we're going to draw on a couple of rules we've talked about so far. The quotient rule and the zero exponent rule. So to explain this one, the negative exponent rule, let's first consider 1 over a to the n. We can rewrite that as a to the 0 over a to the n, because remember, a to the 0 based upon this rule is 1. Okay? Now let's apply our quotient rule to this rational expression here. That is keeping the base a and subtracting the exponent of the denominator from the exponent in the numerator. So we got a to the power of 0 minus n, which is a to the negative n. So we just demonstrated our negative exponent rule there. All right, so these next ones that we're going to explain are not nearly as profound and, in my opinion, not as interesting as the ones we've talked about so far. But let's get to it here. So the one that is very popular is the product rule for exponents, right? So basically, if you got m and n again and they're natural numbers, and you got a base a and it's a real number, then if you got a to the power of m multiplied times a to the power of n, that's going to be equal to the base a to the power of m plus n. So basically, multiplying powers of like bases, you keep the base and then you add your exponents. All right, so what I'm going to show you now is not necessarily consistent with the way that you would do a proof, but the way I'm going to explain this does draw upon some knowledge that we know already, or we should be familiar with. Let's consider x squared. And I think we all can agree that x squared is actually x times x. All right? And drawing on something we've already talked about, remember, any number can be represented exponentially by giving it a power of 1. So x to the first times x to the first is x times x. Now let's try something with this product rule and see if it holds. So what we did was take the like base and then added the two exponents there. And if you look at this, this is consistent with x squared. Okay. All right, so what we have left here are what are referred to as the power rules, and that's where we're headed right now. All right. The power rules for exponents. Notice there's three power rules for exponents, right? Okay. Let's first try to demonstrate the first one here, all right, which is typically referred to as a power to a power, right? So if you look here, we've got the quantity a to the power of m to the nth power, a power to a power, right? And if you look at this, basically that's saying that that will actually be a to the power of m times n. So in other words, when you raise a power to a power, what you do is multiply exponents, okay? Right, again, this is not necessarily a proof, but I think the best way to explain this is to actually use some numbers that we're familiar with. All right, so let's consider 3 squared, the quantity 3 squared to the power of 2. And we'll look at this in a couple of ways here. All right, so if we were just to use our typical definition of an exponent, the quantity to a power is multiplying that quantity times however many times the exponent entails. So basically we're taking 3 squared times itself twice. Then we would use the product rule here, like base of 3, and then we would add our exponents, and that's 3 to the 4th. And 3 to the 4th, on the very basic definition of an exponent, is 3 times 3 times 3 times 3. And 3 times 3 times 3 times 3 is 81. So our question is, can we apply this power to a power rule? Let's try it. All right. So what we're going to do here is multiply our exponents. So we just multiply the 2 times the 2 here. Okay? That 3 to the quantity 2 times 2 is 3 to the 4th. And again, 3 to the 4th is 3 times 3 times 3 times 3, which is 81. So our rule holds using a number here. And you can try it out with other numbers if you would like to. But it does hold, okay? All right, so we'll go to our next one here. Again, we're talking about our power rules. And we're going to talk about the second of the 3 power rules, which is generally referred to as a power over a product. Notice we got a product here, A times B. And basically what we have here is the quantity A times B raised to the power of M. And that equals A to the M, B to the M. In other words, when we raise a product to a power, what we do is raise each factor in the product to the power, okay? So again, what we're going to do is just look at a couple of numbers here and see if this holds true. So, 3 and 2 are some of my favorite numbers to use because, we're all familiar with the multiplications of these particular numbers. So I really like to use these numbers. Anyway, we've got a product here, 3 times 2, the quantity 3 times 2 raised to the power of 2. All right, so let's just use, again, our basic rule of exponents, which when we have a quantity to a certain power, that means we take that quantity times itself that many times. In this case, we take it times itself twice. All right? All right, 3 times 2 is 6, and 3 times 2 is 6. And 6 times 6 is 36. All right? So our question is, can we apply our power rule for a product to a power? All right? That's our question. Let's try it out. So what we've done here is apply the power of 2 to both of the factors here. Notice we took 3 to the second power, and we took 2 to the second power. All right? Again, 3 squared is 3 times 3, and 2 squared is 2 times 2. And 3 times 3 times 2 times 2 is 36. Okay? So, again, our power rule holds within a specific example. And you can try this with other numbers if you'd like. All right, again, now we're going to look at our third part to this power rule for exponents. This one right here. It is typically referred to as taking a quotient to a power. Okay? If you look at it, what we have here is the quantity A over B to the power of M. And that equals A to the M over B to the M. So in other words, what we're doing here is raising a quotient to a power. And when we do that, what we do is raise the numerator and the denominator to the power indicated, right? So again, let's just look at some numbers to see if this works. So again, I got the 3 and the 2. So I got 3 halves squared. All right? The quantity 3 halves squared. So using our basic rule of an exponent, we're taking our base and we're multiplying it times itself twice. Now, what we're going to do is use our rule for multiplying fractions, which means we multiply numerators and we multiply denominators. So 3 times 3 is 9, and 2 times 2 is 4. All right, so our question is, can we apply this power rule here? A quotient to a power, let's just say it that way. All right, so let's try it out. Notice what I did was apply the exponent, or the power of 2, to both the numerator 3 and the denominator 2. All right, so I got 3 squared over 2 squared. Again, 3 squared is 3 times 3, and 2 squared is 2 times 2. 3 times 3 is 9, and 2 times 2 is 4. So again, our rule does hold through a couple of examples using numbers. Okay, so I hope this video has helped with any of those why questions out there. And I hope it goes to the big question of what is the deal with all these rules of exponents.